So not 100% decided, but. Okay, lesson 11.4 is normal distributions. In 11.3, we just talked about distributions in general, right? We talked about data distributions, what it meant to be symmetric versus what it meant to be skewed. And as we look at this idea of a normal distribution, we're focusing in on talking about just the ones that are symmetric. Okay, when we talk about a normal distribution, we are talking about when one is symmetric. Okay, now it falls under something called the empirical rule, and that is what our focus is on today. The normal distribution has a special property called the empirical rule. The approximate percentage of data of values falling in any interval of the range of the data can be determined using just the mean and the standard deviation. Now, some information about this. First of all, before we get going, for population, okay, the mean is usually denoted as, it's another little Greek letter, it's mu. Kind of looks like a little cursive lowercase u, but I believe it is called mu. And the standard deviation is sigma still, and that's the one we've already been using, haven't we? Okay, so when you see those, whether it be in the book, in the homework, in the notes, mu is the mean, sigma is the standard deviation. And so as you look at this, you will notice here that mu, the mean, is in the middle. So this right here, your middle line, is always your mean. Okay, that mean is the average. It should be the middle, especially of a normal distribution. And then each line you go out represents a standard deviation. Okay, so right here is mu, or your mean. When we go 1 to the right, that is going up 1 standard deviation. When we go 2 to the right, that is going up 2 standard deviations, 3 standard deviations, and 4 standard deviations. So now I know the only one that's marked is the mean, and then so this one that's not marked here, this would be your mean plus 1 standard deviation if you want to mark it in there. This is 2 standard deviations, and so what's this one going to be? That's going to be your mean plus 3 standard deviations. So each line adds another standard deviation. What about going the negative direction? The same thing. First line to the left is going to be the mean minus a standard deviation. We've got the mean minus 2 standard deviations, and then this, of course, is going to be the mean minus 3 standard deviations, and the mean minus 4 standard deviations. Now, how this is important. Okay, by the empirical rule, okay, on a normal distribution, or if you ever hear a teacher refer to a bell curve, this is also the idea of a bell curve. 68% of all the data fall within 1 standard deviation of the mean. And that is this piece right here. How far from the mean does a value in a normal distribution fall? So 68% of all values fall within 1 standard deviation. So if you take the mean and you subtract the standard deviation and add a standard deviation, all that information, 68%, will be in that range. Okay? Now the next set out. 95% of all data fall within 2 standard deviations. So you'll notice right here, where this green line is, from here to here, 95% of the data fall. And as you'll notice, it kind of makes sense. In the middle, it's real tall, right? So there's 68%. You get out to here and here. That's going to be 95% of your data, most of your data. And then 3 standard deviations, about 99.7% of all values fall within 3 standard deviations of the mean. With the idea that underneath this normal distribution curve is 100% of your data. Okay, those last little bits are just out here in the end as the tails go out. Do notice this rule applies only to normal distributions. Okay, so as we're talking about the empirical rule, we're specifically talking about normal distributions. So this 68%, 95%, 99.7% rule is for normal distributions. Now, kind of lock those values in your head. We're going to be using them a lot. We're going to be working with them as we try and answer some questions about some normal distribution curves. Okay? So you got the information here, yes? And good news is you can keep going back to it. Now, let's go and look at the bottom of this and look at an example to help us understand it. An example of an early application of statistics was in the year 1817. A study of chest circumference among a group of Scottish men exhibited an approximately normal distribution. So notice they already told us this, right? Normal. Their chest circumferences ranged from 33 to 48 inches, with a mean chest measurement of 40 inches and a standard deviation of 2 inches. Use the empirical rule to help you understand the distribution of chest circumferences in the study. Now, ultimately, our goal is to answer these questions. But before we answer these questions, I kind of want to go through and put some labels on here to help it make sense. So, the mean. Where did I say the mean was going to go? It's in the middle, yes? And what they tell us the mean was? Mean chest measurement of 40 inches. So right there in the middle, that is my mean of 40. And then what else do they give us? Standard deviation of 2. So what's that mean as I move one line to the right of 40? What's that going to be? Add 2, because we're moving one standard deviation over. And so if we add 2, that puts us at 42. So that is adding 1 standard deviation. What's the next line? 44. Because what are we doing? We're at the mean, we're adding 2 standard deviations. And so 40 plus the first 2 is 42, plus the next one is 44. And of course, what's this next line going to represent? 3 standard deviations or 46. You realize up there when I say plus 1, plus 2, plus 3, I'm attempting to make a little sigma, yes? It stands for standard deviation. That's what that is saying up there. What about when I go the other way? We're subtracting our standard deviation of 2, yes? So 40 to left is going to be 38. Another standard deviation left is going to be 36 and 34. So that is going 1 standard deviation left, 2 standard deviations left, and 3 standard deviations left. Okay. Now, I think I have all the information I want on there for right now. Are you okay with how we filled this out? I see it as kind of easy, but I want to make sure you guys see it as kind of easy. Okay, we'll look at A. What range of chest measurements contains the 68% which fall closest to the mean? I agree. Why?
Because it's within the plus 1 standard.
Yeah. If you go back up to the top, the 68% should sound familiar, shouldn't it? That's part of our empirical rule here, is that 68% of all values fall within 1 standard deviation. So when we go to look at ours, where is 1 standard deviation? Right there from 38 to 42, yes? So the fact that it asked for 68%, well, that means we're going plus or minus 1 standard deviation, and that is 38 to 42 inches. Okay. Questions on A? Okay. So B. What would you expect the chest measurement to be for the 2.5% of the men with the smallest chest measurements in the population? Two and a half percent, the smallest chest measurements. Any thoughts? What?
Because minus 2 is 36.
No. Minus 2 standard deviations is 36. This is 2.5%, not 2.5 standard deviations. What?
34. Because it's the smallest measurement.
No.
Is it 33?
No.
Is it higher or lower?
I think we're just guessing at this point.
31.
Again, I think we're just guessing at this point.
Well,
Hot or cold,
it
32.
says that their chest circumferences range from 33 to 48. So then
33 and a half.
Okay. What other percents were we given besides 68%?
95 and 99%.
Okay, 95 and 99.7. Let's look at that 95. What is that? Where is that 95?
36 to 48.
Within 2 standard deviations is 95%, yes? Are you following me here? If 95% of the information is between 36 to 44, what is outside of the 36 and 44? 5%. What would we assume about that 5%?
2.5 minutes.
Split it in half, and that's 2.5 on each side. Are you seeing this? Okay, so the idea that if here to here is 95%, we've got 95% in the middle, this all adds up to be 100%, well, that means there's an extra 5%, yes? That extra 5% is going to be split into the 2 halves, which is 2.5 and 2.5. Is that math making sense? So the idea that if this is 95%, I'm trying to think, what else do I need to draw on here? Am I okay to? Then that means over here on out is going to be another 2.5%. And here on out is going to be 2.5%. Because now in green, do those all add up to be 100%? Okay. They're going to throw some numbers at you. They may not be percent numbers that they give you, but they all relate back to that 68, 95, and 99.7, somehow or another. So, what would you expect the chest measurement to be for 2.5% of the men with the smallest chest measurements? What are we going to say at this point?
35, 36. 36.
I was going to say,
33, 36.
okay. On my paper, I wrote less than 36. Now, what did they say here? They range from 33 to 36, so or 33 to 48. So if you said 33 to 36, that would make sense as well. My paper, I just put less than 36. So I'm going to say less than 36 inches. And I guess in my brain at the time, I was forgetting that they gave us a small end, didn't they? They told us that it meant their minimum is at 33. So had I thought about that, I might have said 33 or 36. Both answers work in my opinion. You know, if Saba says something like that, just beware. They could go either direction, I would say. Okay, did we catch up with that one eventually? Mathematically, it makes sense. You just have to see it. Okay. Well, start looking at C when you're ready. What would you expect to be the smallest and largest chest measurements of the middle 95% of the men? This one isn't too bad, actually. Yeah.
36 and 44.
Yes? Because 36 and 44 are right there at 2 standard deviations, right? When it's asking for 95%, realize that is plus or minus 2 standard deviations. And so smallest would be 36 inches, largest would be 44 inches. Okay. One more. What would you expect to be the measurements of the 16% of the men with the largest chest in the population? So we're looking for the top 16%, or 16% largest. Where does 16% fall in here?
Would it be 44 and 48?
No?
Would be 44, 46.
No?
46
No?
44 in the book.
Nope.
Would it be 42 and 48? That
Why?
makes sense, because there's 32 left of 100%, so there's 16 on each side.
Okay. Are you seeing this? So it kind of goes back to what we did here, except now we're talking about the 68%, yes? So think with me here. If we've got 68% in the middle, right? What is, this is what I did on my paper, I said, okay, what is 100 minus 68? And 100 minus 68 is 32. What is 32 when you divide it into 2 for each half? 16. So that means you're going to have 16% when we divide it, just like earlier, right? When we had 5% left over, we had 2.5, 2.5. Same thing here. This time we have 16 and 16 left over. And so we want to know the 16% with the largest, so we want to know the 16% up here, which, I don't know if it helps. Here's 68, yes. And so then that means the 16% is going to be there, and are you seeing that setup now? This graph divides in so many different ways, doesn't it? But so then our key number here, we want the top 16%, it's going to have to be 42 inches or greater. And again, 42 to 48? Yes, because 48 is our max here, right? Okay, are you starting to see this a little bit? Maybe? I know, it's going to take some practice, right? Figuring out all these numbers. We're going to practice some more on this next page. Recent SAT scores for college-bound seniors are normally distributed with mean score 508 and standard deviation 121. How does the empirical rule help you understand the performances of individual students? Now, we have some ABCD questions again, right? My recommendation before we jump into those questions, can we set up our curve here, our distribution? What goes in the middle? The mean, which is 508. Okay. What now? What? Yeah, add 1 standard deviation. You take 508 and add 1 standard deviation, we're going to be at 629. So 629 is that number, right? How do you get the next number? Add another one. What do we end up at? 750. How do we get the next number? Add another standard deviation. 871. Do we have to show all that work? No, I'm just putting it there because it might help you later when you look back and say, where did these numbers come from? What about when we go left? Yeah. Start with your mean, subtract 1. 508 minus 121 is 387. Keep going, yes. Subtract another 121, and we end up with 266. One more time. We end up at 145. Okay. Can you answer the first question? What proportion of students receive scores between 387 and 629? And why 68%? Yeah. 387 and 629 are 1 standard deviation above and below, yes. And the rule is 68% of our data is within 1 standard deviation of the mean. And so the 387 is 1 standard deviation to the left. The 629 is 1 standard deviation to the right. And so since those are 1 standard deviation left and right, that does put me at 68%. Okay. What proportion of students receive scores greater than 387? What?
95.
No. I can go for 84. How can we get 84?
That's 16 from the 620.
Okay. So there's different ways that we can think about this. Okay. Stetson looked at the fact that my middle 68% is here, yes. And if my middle 68% is there, I'm trying to think how I want to do this, then what is left on either side? 100 minus 68 on the front side was 34, right? 34 divided by 2 is going to be or excuse me, 32. Yep, thank you. Right? If you have 68% in the middle, in other words, 100 minus 68 is 32. 32 divided by 2 is 16. So that means you have 16 on the left, 16 on the right. Where was 387 at? 387 is right here, isn't it? So then that asks us, what is 68 plus 16, which is 84%. Anyone else do that a different way? I had a different way that I thought about also. .508 marks the what? The middle, yes? So above 508 is going to be 50% of the data, and below 508 is going to be 50% of the data. So could you think in terms of to the right of 508, that's 50%, yes? Plus, what do you have right there? Are you seeing where I'm going with that? That's 50% to the right there. And then this is going to be whatever, it's going to be 68 divided by 2, because 387 to 629 is 68. And so that's going to be 34%. That's like, nope, I liked my way better, which is fine. And here's the deal. It goes with whatever you see, right? The reason I mention both is because if you like one better than the other, you know. So either way, it is 60 or it is 84%, isn't it? Are we okay with that? You guys are quiet. I don't know what to think about this. You're always quiet. Not surprised, but okay. Let's try C then. Stop me if you have questions, or if you need me to try and explain it a different way. I will gladly make the best effort I can. C. Find the proportion of students who earned SAT math scores between 266 and 750. This one's too easy, isn't it? After the one we just did, this one's a piece of cake. Are you guys seeing it? What do you notice about 266 and 750? That is my plus or minus 2 standard deviations, which is 95% of the data, right? So since that is plus or minus 2 standard deviations, that is 95%. So if you just know the basics there, you can get that one. Okay? Proportion of students who earned SAT math scores between 266 and 629. No. I will say that was the common wrong answer in my morning class. I'm trying to remember how they got it, but so we're doing 266. Sorry, I know it's getting very colorful here, but I have to, so many numbers there. Okay. Katie, you said 68 plus 8, right? And why did you do the 8? Because you looked at the fact that there's 16% down here, and you took that 16% and divided it in half. But these sections aren't equal, because these sections get shorter and shorter and shorter. Okay? They may be equal in width, but that doesn't mean they're equal in percentage. Thoughts on what to do here?
be 87.
No.
79?
No. Okay, now you're just guessing numbers. There's a decimal involved in this one, so we don't want to just spend all day guessing. What do we know? We're trying to go from, what is it, 266 to 629. What do we know within this piece? We know from 387 to 629 is how much? 68, yes? What's the difference between going from 387 to 266 in terms of percents? Well, okay, so in terms of, what is 95 minus 68, right? That's the direction we need to head. What is 95 minus 68? 27%. Now think about it. What is that 27%? Oh wait, I don't want to do that because that's going to make it think.
750.
Okay, we got, oh, shoot. Come on. We got 68% from 387 to 629, yes? Then out here from 266 to 750, we have 95%. 95 minus 68 is going to be 27%. Where is that 27% going to be split? On each side. And so what is, I didn't leave myself enough room, 27 divided by 2? 13.5. So what goes in each of those pieces? 13.5. Are we seeing that? Because earlier, like Katie, I know, and I know she's not the only one, she just took the fact that there was 16% on that left end and broke it into 2 equal pieces. But it's not equal pieces because these pieces are getting shorter and shorter and shorter. Okay? So, here. I'm bringing my numbers over here because that graph is getting very difficult to read, yes? So from here to here is 68%. From here to here is 95%, right? So right here, across the middle, 68%. These extra 2 pieces right here are going to be the 95 minus 68. So 95 minus 68 is going to go in those 2 pieces. And that 95 minus 68 is 27. If I take that 27 and divide it amongst the 2, that puts it at 13.5 in each of the 2 pieces. Okay? And this whole time, what did we need? We needed 266 to 629, so we need the 68 and the 13.5. And 68 plus 13.5 puts us at 81.5%. Have I sold you? Some yes, some no. This may take some work. I'm learning as I go here. You want honesty? I can't say I've ever taught this lesson. 23 years of teaching and I have never taught normal distribution, so I may have to get creative here. Okay, I promise it's all about the numbers. It's all about looking at that 68, 95, and we didn't even really use the 99.7% today, but it's all about using those numbers, okay, and looking at the differences between them. Are there any questions you want to ask? Because I am more than willing to answer questions. Yes.
I did it a completely different way, but I still got the same answer.
Okay.
I took the distance between 750 and 871 is 2.5, and then no, I actually don't know what I did.
It made sense at the time.
I got 2.5 from on the right side, and then on the left side I got 16%, and then I added those two together and I got 18.5, and I subtracted that from 100, and then I got 81.5%.
Oh, so you took, okay. I see what you did. You took, so the whole thing being 100%.
Yeah.
So over here, you would be taking, I'm going to use, so over here, you took this 16% off, is what you did. And you took, wait.
No, it's the opposite. I took from 629, and then the distance between 629 and 871 is 16.
Okay, there we go. Okay, so here. So this is, you looked at this being at 16%. I've got it now. Right? Yeah. I think. And that's 2.5%.
Yeah.
So together, the extra stuff is 18.5%. And 100 minus 18.5% is the 81.5%. Yeah, I see what you did. It's legitimate. You're good.
Okay.
And it's all about breaking the pieces up. Okay? And it's going to take some practice, I'm telling you. I'm seeing that. So, okay. Where are we at time-wise? About 5 minutes left. Okay, we're going to talk a little bit about z-scores on the bottom. And then we'll have to finish talking about z-scores tomorrow, because we're not going to get all the way through it, obviously. When we talk about z-scores, how we will use z-scores. Our z-scores gives us a way to compare two sets of information that is not the same. Okay, so the z-score counts how many standard deviations a value is above or below the mean. So I could be looking at two totally different sets of information and compare that, okay, well, that person has a score 2 standard deviations above the mean. Well, this person's score is 1 standard deviation above the mean. That's what that z-score tells me, is where is the score in relation to the mean and standard deviations. Now, z-scores can be used with any distribution, whether normal or not. But here's how we'll find z-scores. The math is very easy behind it. Just the data value minus the mean divided by a standard deviation. And what it will give us is a way, for instance, in this example, to compare Ella and Alicia's scores on 2 different college entrance exams. Okay, you guys are familiar with the SAT. My morning class seemed clueless about the ACT, which it used to be a very common college entrance exam along with SAT. But have they done away with ACT? I don't know. So, but their scores look totally different. You guys are familiar with SATs. SAT scores are in the hundreds, right? ACT scores look more like your ASVAB scores. So how do you compare and say, well, who did better? Who got the better score when they're 2 totally different things? And that's what a z-score will allow us to do. So we'll look at this problem. I think I'll just wait till tomorrow at this point with Ella and Alicia, okay? We'll go through there. We'll do some comparison. We'll talk about how to do z-scores and also how to turn those into percentages, okay? But I think I will stop there because I'm going to get in the middle of this problem and get caught.